All right, I got a request to review the quiz, which I don't normally do with online quizzes, but we would normally do if we were meeting in a classroom. So I figure why not? It's a little different, and you get a peek behind the scenes of what the quizzes are like to put together. Uh, as you know, there are different students get different questions. So all the quiz questions are divided up into groups, or you can do it that way if you want to. So this is how I do it. So you may see some questions as we go through this that you did not get, or you will see questions that you did not get. But we'll go over all of them. So you could have gotten for question number 1, if there is good ventilation, then there should be low partial pressure due to oxygen. This should be false, and yay, it is. My key is correct, right? So ventilation just means airflow. The air that you breathe in should contain oxygen, or does contain oxygen. So there would be high partial pressure due to oxygen, which means the alternative question, true or false, should then be true. If there is good ventilation, there should be high partial pressure due to oxygen, and that is true. So if question number 2, possible question, good ventilation of alveoli should cause vasoconstriction in the arteriole, should be arterioles, supplying the alveoli. So this should be, now I need to reread the question again. Good ventilation, this should be false. Make sure I keyed it right, and it is. Right, so if an alveolus or some alveoli are not well ventilated, there is not a lot of oxygen in those alveoli to be had, so there's no point in sending a lot of blood to that alveolus. So what you want to remember, 2 things. One is that this is ventilation-perfusion coupling, whoops, sorry, can I move that? There we go, is a localized effect. So you're talking about if you have differences in ventilation in one part of a lung versus another part of a lung, or one alveolar sac versus another alveolar sac, so these alveoli versus those alveoli, you're talking about where you send the blood, not how much blood are you sending to the lungs based on how much air is there, but where in the lungs are you sending the blood. So you want to send the blood where there's more oxygen. So more ventilation. Let's go with this one first, right? More ventilation, lots of air, means increased partial pressure due to oxygen. This is what the smooth muscle in this arteriole is actually measuring. It has chemosensors that can sense oxygen levels, or partial pressure due to oxygen. So high PO2 means vasodilation, send more blood to the alveoli that have more oxygen. If you have less PO2 and a fully perfused alveolus, or fully perfused alveolar capillary, so lots of blood going to an alveolus where there is not lots of oxygen, then you would get vasoconstriction, so that you're not sending blood to a part of the lungs where there is not a lot of oxygen availability. So then this question, good ventilation of alveoli should cause vasodilation, should be true. And it was. So I think you'll see as we go through this that the questions all align with the material. The material is tricky. The questions are not necessarily tricky, but they are easy to misinterpret because the material is complicated. Let's see. Decreased affinity of hemoglobin for oxygen will lead to, should say, an increase in the delivery of oxygen to that tissue. This is a true statement. And there we go. It is keyed as true. So for this, what you need to remember, and let me delete all this stuff. Sorry, I had to pause it a second to start drawing some stuff. So what you want to remember is that the oxygen is carried in your red blood cells. The red blood cells are in blood vessels, and they stay in the blood vessels. So all these little red blood cells here are where the oxygen is if it is stuck to the hemoglobin. So the red blood cell stays in the blood vessel, the hemoglobin stays in the blood vessel. So you need the oxygen to let go of the hemoglobin if it is going to enter the tissues that actually need it. In this place we've got cardiac tissue, and you can see it is very well highly vascular because your heart needs lots of oxygen. So the hemoglobin stays inside the red blood cell stays inside the blood vessel. The oxygen has to get out of the blood vessel to the surrounding tissue. In order to do that, right, it needs to let go of the hemoglobin. Affinity means stickiness, how tightly the oxygen is stuck to the hemoglobin. If you are going to deliver it, it needs to become unstuck so that it can go from the red blood cell into the tissue that needs it. So if it's less sticky, then more oxygen is delivered to the tissues. So then when you're thinking about highly metabolic tissues, you always want affinity or stickiness to be low. And affinity sounds like a good thing. You want lots of oxygen in that tissue, so you're thinking the affinity should be high. But the problem is the affinity is in the bloodstream and keeping the oxygen in the bloodstream and not delivering it to the tissues. So it's kind of exactly opposite how it sounds. But you just have to remember the relationship between the blood and the tissue, and you have to get the oxygen out of the blood. So then when you're considering all of this stuff, you just want to think to yourself, well, what should be the conditions in a highly metabolic tissue, right? Should there be lots of oxygen or not? Should the temperature be high or low? What should the pH be? And then adjust the affinity accordingly. So the other thing to remember with all of these intimidating graphs is that your body works. It doesn't always make sense, and maybe you are primed to think that things are trickier than they have to be, so you don't want to take the obvious answer, or you don't trust yourself to logically arrive at the proper answer because you think you don't know enough. But in this classroom, or in this class, if you remember everything I say, you do know enough to answer anything that I ask you. So there are tricky topics, but no trick questions. So I'm just going to go through this before we go back to the quiz because I'm here on it. And I'm not even going to go to the graphs because I think the graphs, I always include them because I'm a nerd. But if you're not a nerd, they get confusing. So let's just say highly metabolic tissues, oxygen levels should be low, right? Because the tissue is using all of the oxygen. You might want the oxygen levels to be high because the need for oxygen is high. But there's never going to be a lot of it lying around because it's always getting used. So that means if you have low PO2, then you are going to want decreased affinity because that means that more oxygen is going to be delivered to the tissues that need it, and you're alive, so that's what's going to happen. Like your body works. So let's look then at temperature. You all hopefully intuitively know that when you exercise, you sweat because your body gets warm. Heat is a byproduct of your metabolism. So if the temperature goes up, as it does in highly metabolic tissues, then affinity is going to go down. And then for pH, again, I say just think about when your muscles go anaerobic, they release lactic acid, and then that would lower the pH. So if you have low pH in a tissue, that is indicative of increased metabolism. So you are going to want decreased affinity of hemoglobin for oxygen so that more oxygen leaves the bloodstream in the tissues with the lower pH, the higher temperature, and lower partial pressure due to oxygen. And that's all these slides say. So just pay attention to the affinity part, not the graph if the graph does not help you. But I myself like the graphs. So then let's just go back to the questions. If we increase the temperature in a tissue, this will lead to an increase in the affinity. That is wrong, right? We want a decrease in the affinity. We want hemoglobin to let go of the oxygen, so that is false. If we decrease the pH, this will lead to a decrease in the affinity. This is true, right? Low pH means increased metabolism, so we want lower affinity of hemoglobin for oxygen so that hemoglobin will let go of oxygen in the tissue that needs it more. So that is a true statement. Let's see. Then, how is most of the CO2 transported in your bloodstream? As bicarbonate in the plasma, this HCO3 minus ion. And we'll go back and go over the PowerPoints for this. The CO2 converted to carbonic acid in your red blood cells does not affect the pH of blood. This is true. There we go. True. So let's go back and talk about those, which is here. So the first one is just right here. 7 to 10% is dissolved in the plasma, so that's just CO2 in the plasma. 20% is bound to hemoglobin, that's this stuff right here. That's your 20%. And then 70% is transported as bicarbonate in the plasma. That's this slide right here. So we're talking about this is your 70% of CO2 that gets converted to carbonic acid, which then falls apart into this hydrogen ion and this HCO3, the bicarbonate ion. That gets pumped out of the cell and is transported in the plasma as bicarbonate HCO3 ion. This carbonic acid does not actually lower the pH in your red blood cells because this hemoglobin here, when it lets go of that oxygen there, is going to pick up that hydrogen ion. So you have hemoglobin essentially buffering or absorbing hydrogen ions from carbonic acid so that the CO2 that you transport in your bloodstream, or this 70% here, doesn't lower your pH. Then you do need to remember that, so where are we? Yeah, so this HCO3 becomes your alkaline reserve. That's a separate topic. This 7 to 10% CO2 here that dissolves in the plasma, that does affect your pH because there's no hemoglobin in the plasma to buffer or absorb those hydrogen ions. So this does happen at a relatively slow rate because there's no carbonic anhydrase no enzyme to catalyze this reaction in your plasma, but CO2 dissolved in the plasma does get converted to carbonic acid, and that carbonic acid can lower the pH in your bloodstream. Under normal breathing circumstances, it doesn't. So your tidal volume and stable physiology means your pH stays stable. If you have increases or decreases in your respiratory rate, big changes, then that can affect your blood pH. And then that's where we get into this stuff here. So if your physiology remains the same, but for some reason your respiratory rate changes, you start hyperventilating because of anxiety, or you just can't breathe well, you're having an asthma attack, then changes in respiration cause changes in how much of this pool of CO2 is in your bloodstream, and that can cause respiratory acidosis or respiratory alkalosis. We'll just go over the whole thing because we're here. I was going to make a separate video for this, but I've come this far. So where are we? Right, so it's CO2 that we're worried about. If decreased respiration, you're having an asthma attack, your airways are constricting, you cannot exhale CO2 as efficiently, your partial pressure due to CO2 is going to go up. So this pushes the chemical equilibrium in that direction. So CO2, I'm just going to write CO2 and H plus. Whoop, the plus is supposed to be up there. Right, there are two equations here. There's the equation around that arrow and the equation around that arrow, but they're all connected. So again, remember that there is always a constant ratio of how much is here versus how much is there. Not necessarily equal amounts, but whatever ratio there is at equilibrium, this is what the chemistry is always going to try to get back to. So if you... Oh, why is my battery device low? It's plugged in. I think this is what happens when you're working from home forever every day and your laptop is plugged in pretty much 24/7. The battery gets messed up. So you're you're loading CO2 onto this side of the equation. That causes an imbalance or changes the ratio of what's here versus what's there. So the chemistry moves in that direction. So more CO2, more carbonic acid, more hydrogen ions, pH goes lower. And then if you just start hyperventilating for some reason, there we go, right? Now you're unloading stuff from this side of the equation. You are getting rid of more CO2 than you normally would. So the seesaw is going down on, whoops, I did it wrong. This side is getting heavy, right? So the seesaw is going down this way. You want this end to come back up, or you want to bring this end down. Now I'm just scribbling all over the place. Low CO2. So if we want to restore the ratio of hydrogen ions to CO2, we need to move the chemistry in that direction. So that means hydrogen ions and bicarbonate get back together to form carbonic acid, which then falls apart to make more CO2. Again, because there's always a balance or equilibrium across this equation and that equation, so they all have to be in balance. So if more hydrogen ions are being bound up in the undissolved acid, then the pH goes back up. So this relationship is always the same, in that if your respiration rate goes up, that's going to bring your pH down. If your respiration rate goes down, then your pH is going to go up. In this instance here, your physiology is constant, you're in homeostasis, your respiratory rate changes and knocks you out of homeostasis. Then, sorry, let me fix some stuff here. Here, if you're talking about a respiratory response, now you're saying, you're in homeostasis. Something happens with your metabolism to knock you out of homeostasis. So your bloodstream, due to metabolic reasons, becomes too acidic or too alkaline. Then your respiratory system can respond to this change in pH and return the pH to the normal homeostatic value. The relationship between respiratory rate and the direction of pH change stays the same. It is just now you're changing it back to normal instead of knocking it out of normal. So if you are in acidosis, if your bloodstream is acidic because of your metabolism, that means your pH is low. So you've got lots of stuff here. You want to move in that direction, so you need to get rid of CO2 to make the chemistry move in that direction. So you increase your respiratory rate, which is going to cause then an increase in pH. So just like we saw here, if you increase your respiratory rate for no good reason, your blood pH goes up. Here you're doing it to restore proper pH. And then, let me just delete some things. Delete. So, again, everything is fine, and then your metabolism goes and causes alkalosis. Now your blood pH is higher than you want it to be, meaning you don't have enough hydrogen ions. You want more of them, so you need to move the equilibrium in this direction. You want the chemistry to run from left to right. So you need to load CO2 onto this side of the equation, which will push this equilibrium in that direction, forming more carbonic acid, which will then push this equilibrium in the right-hand direction and make more hydrogen ions. This will bring your pH back down and restore proper levels. I hope that maybe helps a little. It's just, like I said, some complicated physiology to remember. That is it. I'm going to do actually one more thing. There wasn't a question on the quiz, but I feel like I should talk about it. Remember your partial pressure gradients for external respiration and internal respiration. When you are reading questions on the exam, the first thing you want to do is say, oh, are we external? Are we internal? Are we in the lungs and exchanging gases with the air? Or are we in a tissue and it's muscle exchanging gas with the bloodstream? And then you just remember what you think should happen, or what you intuitively know should happen, and then you make the partial pressure gradients match the flow of gases for you, remembering that you're going to blow the gas from a high pressure system into a low pressure system, or from an area with high pressure to an area of low pressure. So you don't make the pressure high where you want the gas to be. You make the pressure high in the opposite compartment, which will push the gas into the compartment where you want it. So, right, external respiration, you are exchanging gases with the atmosphere. You want to exhale CO2. So you want higher partial pressure of CO2 in your blood, right, so that CO2 gets blown into the air. And then conversely, you want oxygen to flow into your bloodstream. if something is going to flow down its partial pressure gradient, you're going to have high PO2 in the air and comparatively less oxygen in the bloodstream to get oxygen into the bloodstream. And then when the bloodstream is exchanging gases with your tissues, everything is opposite, right? Now your tissues need the oxygen. So you're trying to get oxygen out of the bloodstream. So you want pressure higher in the bloodstream than in the tissues so that oxygen can blow down its concentration gradient into the tissues. All right, and just think, like, what is the source? Is another way to think about this. And the pressure is always going to be higher at the source. So for your tissues, blood is the source. So pressure is always going to be higher at the source, right? Chances are the store is always going to have more of something than you have at home, unless you went and bought like all of the, I don't know, all the tortillas at the store. Don't ask me why I've got tortillas on the brain right now. And corn, I prefer the corn tortillas to the flour. At any rate, nobody cares. Right? So if you're talking about CO2, what is your source of CO2? It is your tissues. They're making the CO2. So it's going to be high in the tissue, comparatively lower in the bloodstream, so that it will flow from an area of high pressure to an area of low pressure. And going back to the lungs, just to use this whole source thing again, right? For your bloodstream, the air is where you get your oxygen, so that's where the pressure is going to be highest. And then the CO2 you're exhaling, right? Your bloodstream is the source of CO2. So it is, what am I trying to say? The partial pressure of CO2 is going to be higher in the tissues. Sorry. I just got a message on Teams and it's totally messing with my brain. CO2 is going to be higher in your bloodstream so that it flows into the air. That is that. 27 minutes, but we reviewed a lot of stuff. So kudos to you if you stuck around this long.